I'd like to sort of go through today the journey that Paragraph's had from the emergence from Cambridge University to where we are now, scaling up that business in Cambridgeshire based on 2D materials. And this is an educated audience here, and I didn't want to open my talk with references to Moore's Law, and I don't need to explain we've heard a lot about AI and the performance challenge that we have ahead in the industry. I've kind of made a different flavor here that I think for this talk, in that I think the number of presentations that are talking about the end of Moore's Law doubles every 2 years. And I don't want to say more than Moore's Law later on over drinks. But rather than just discussing, as we do as engineers, the performance challenge that we have an equal, if not more pressing, energy-related challenge. We heard earlier about the data center, power consumption. And the colourful chart on the right, which unfortunately is a rather illegible scale, but what the colours there represent, from the red and the yellow, those are the energy consumption from the devices that we carry, the things that we use. And as the performance of our chips and our devices improve, we've done a pretty good job at keeping the energy consumption within those devices in check. But the blue part is network infrastructure. That's the connectivity. That's enabling those devices to connect to the outside world. And the green part being data centers, the cloud, where that data's going. And it's that network connectivity and the storage of that data that has that exponential growth now. So by way of a sort of a background to the 2D material technology that I'll talk about here, we have as much an energy challenge as we have a performance one. So to try and back that up and put some context, I searched up some completely unverifiable stats to put it in context, and already estimating that 20% of energy in computing by 2030 seems like an incredibly frightening statistic, if it's true. There are references to these. And already, global data centers add up to more energy consumption than the entire UK. So I've added in the bottom there that we talked about AI, ChatGPT, and how much even that, there's 5 times more power used in a GPT query than there is a Google search. So I urge you not to check my facts now, as you're just making the problem worse. It's not just computing that has that sort of energy or environmental challenge. And one area I'm really keen to bring up was healthcare. One area of the sort of global industry that you don't normally attribute environmental issues to. But if you were able to, and who brought up this stat, I'm not quite sure, but if you were to put the healthcare sector to create a country, healthcare land, it would be the 5th largest polluter in the world. And a lot of the challenges in that area are, as I've said, over-diagnostics and transportation. So over-diagnosis is really the treating of conditions that you're not necessarily certain the patient has. So a classic example is over-prescribing of antibiotics. That's not just not good for the patient outcome, it has a significant environmental impact. Transportation is either getting patients to the healthcare setting, doing tests, getting those test results to the lab. That transportation impact is significant. So our industry has a part to play here, I believe, in bringing point-of-use diagnostics, for example, to the patient, removing the transportation issues, and bringing not just better patient outcomes, but the environmental side of that too. There are lots of solutions for both the performance and the energy challenge that I'm talking about. Obviously, from Paragraph's perspective, I'm going to talk about two-dimensional materials and their parts, the part that they have to play. And you hear a lot about, and we talk a lot about the superpowers of two-dimensional materials in Paragraph. And if you just take some of those in the context of this audience, thermal stability and in particular high conductivity, then those things relate in the right device environment to significantly enhance performance. And even a pretty mediocre graphene layer is about 150 times more conductive than silicon. And while that in its own is another interesting stat, that then can be converted into a relative performance improvement where it's applied. 2D materials are not just graphene. Graphene is that single atomic layer of carbon. It's the elemental 2D material. But the 2D materials have the same kind of roadmap that silicon and compound semiconductors have, in that binary materials, multi-plane 2D, which sounds like a contradiction, but it's effectively a building up of a layer from individual 2D planes, offer the same sort of roadmap as going from silicon, gallium arsenide, tertiary, quaternary materials that the compound semi-industry is used to. So graphene being the first one is just our first step on that two-dimensional material roadmap. The last selling point on 2D materials, particularly on the environmental side of things, is that by its definition, it's incredibly thin. And as a semiconductor industry, as electronics industry, we kind of got used to the raw materials that we use being particularly expensive, often toxic, difficult abatement and environmental solutions to them. By implementing 2D materials where we can, not only is the volume of raw materials reduced, but also the toxicity, in the case of graphene, for example, is removed. I was once asked whether you could actually eat graphene, which I wouldn't recommend, but the toxicity of it is not the same as you have with compound semiconductors or the precursors used in silicon, for example. So better performance, low toxicity, lower amount, what's not to like, okay? So now I've convinced you that 2D materials are a significant part to play in the challenges ahead. What are the challenges of bringing that new material, that emerging technology to the industry? And the most striking thing is how long it takes to bring a new material to the industry, how long it takes to change the industry to adopt something new. And I pulled up something from the Hansard and the House of Lords debate from May the 2nd, 1986. 86. This is Margaret Thatcher's government. Lord Birdwood here, unfortunately you can't read that, but Lord Birdwood raised a debate talking about generating UK government support for the new material gallium arsenide, which takes over from where silicon leaves off in 1986. Unfortunately, Lord Birdwood isn't with us anymore. I'm sure he'd have a lot to say about the compound semiconductor catapult and the new UK semiconductor strategy if he was still around. 38 years after that debate. So we have a significant time challenge and period of time that it takes to bring a new material to the industry. And it's not just pioneering the technology that's required when you're bringing adapting an emerging technology into the industry. You have to demonstrate that manufacturability. Being able to produce something in the lab doesn't mean that it's commercially successful or scalable in production. Because you've made a new material doesn't mean that you can necessarily incorporate it into a useful working device. You have to, I guess, do what I'm doing now, and that is communicate the needs and the performance of this new technology to the industry, create the roadmap, and develop as many partnerships as you can along the way. And not to mention building a factory or two. You can't develop a material in the lab and go to a foundry and say, can you produce this new material for us, please, or can you process it for us? You have to do it yourself. You have to build that manufacturing capability, that production capability within and under your own roof. And as a startup business, that's quite a challenge. So what is that disruptive material technology? If you go back 20 years, University of Manchester, the first isolation of graphene was nothing more than sticky tape and a block of graphite. So to produce that single atomic layer of carbon was produced by continually removing the black carbon from a block of graphite until a single atomic layer was isolated. If your kids come home needing to do a science experiment on the weekend, then I'd recommend this one. You just need a pencil and a roll of sticky tape, and you can have the whole rest of the weekend off. Nobel Prize in the post. while that's great for the science and the discovery, and it proves that the material's possible, from an electronic standpoint, we needed to find something which was much more manufacturable, something that we recognize. And the industry originally, or initially, honed in on what's called transferred graphene. So to produce graphene, in this case, to get that single atomic layer, you needed a copper catalyst to deposit that carbon layer on, and then use an array of polymers and etchants to remove the copper and the polymer and isolate the single atomic layer of graphene, and then mechanically, physically transfer it to the silicon substrate. So I like to call it graphene fishing, if you like. And if you've ever done an airfix model and had tried to move that sticker, the decal, from the piece of cardboard onto the wing of your Spitfire without tearing it, you know, and everyone's going, yeah, I feel that. Imagine that sort of an 8-inch diameter, 1 atomic thick decal that's almost completely invisible. And it's no surprise that while great strides have been made to produce this transfer graphene in some reasonable scale, it's not surprising that the repeatability and the scalability of using this approach has proved difficult. Paragraph's approach is not particularly controversial to the industry. We're using MOCVD. It's actually the same thing that the compound semiconductor industry has used for decades. It's not easy to produce and stop at a 2-dimensional layer by that method. It's a process which has taken many years to perfect, and we're still perfecting it, not just for graphene, but for other 2Ds. But what it gives you is a removal of the issues that come with fishing or transferring. You know, the damage is reduced, the contamination is reduced. Most importantly, it's cost-effective and scalable, just like mainstream semiconductor materials are. So no sticky tape here, no buckets of acetone. An MOCVD reactor, in this case, one that was rescued from a humble life producing gallium nitride LEDs. Month after month, we've repurposed it into now forging ahead, producing graphene. A much thinner and a nice retirement for a gallium nitride LED reactor, and is now the workhorse for some of the R&D that we're doing in Cambridgeshire. So developing the material is fine, and that's the first most important building block, but you can't stop there. If you're building a business that's going to commercialize that material, you need to do more. You need to build a whole ecosystem from the device design right through to the final product. For the reasons I said before, you can't go to a foundry and say, can you process this new material that I've just produced? Because if they let you in the fab to start with, they then don't know what to do with it. So contacting a 2-dimensional layer, for example, is quite tricky. A metal contact on something that doesn't have an edge is a challenge in itself. And graphene is as influenced by what it's put on and what's put on top as it is the quality of the material it is. It's effectively a surface. So the development of the whole layer stack, not just the 2D layer, but what goes around it, is really important. So Paragraph's efforts have gone into not just the material design, but everything around it, and creating a whole array of IP and know-how in the process. So this is becoming a business now. If I was to stand here and say that we have an aim to produce 2D processing capability in 10 years' time, and I'm looking for investors to be with me along that journey, then that will be one hell of a challenge. Okay, we're not going from here to something 15 years' time without anything in between. It wouldn't work. What we're doing is building process IP, building know-how, and producing product stepping stones along the way, starting from relatively modest device complexity. And in the first case, the product that we released a couple of years ago was a Hall effect sensor. The most straightforward of architectures. It's a Hall cross. But in the case of getting a graphene version of a Hall effect sensor, then there's a lot of know-how and IP to get and isolate that layer, get the right layers around it to contact it, and make it repeatable and scalable. And that product is in effect a validation technology. It shows that we're not producing lab results. We're producing products that you can buy in volume and they're the same time and time again. And they have found unique sort of selling points, or if you like, use cases where the traditional Hall effect sensors based on silicon or gallium arsenide or indium antimonide start to tail off. So graphene operates at millikelvin temperatures. It's the only material that will go down and measure that low temperature. So use cases in dilution refrigeration, so quantum computing and things like that, where measurements under those extreme environments are important. Being two-dimensional, it only actually senses in the plane that it's pointed at. It has no third dimension. So if you're measuring, in the case of a Hall sensor, a current, using it as a current sensor in a particularly noisy environment, that magnetic field that it's measuring is purely in the plane of the 2D material, no noise or interference from anything else. So electric vehicle is basically a large electromagnet on wheels now with noisy environment, so it's becoming more and more of a challenge to measure actually what it is that you want to measure. For example, leakage currents in EV batteries. We continue to develop those building blocks, that process IP and knowledge to get towards a transistor. And the second device, which is called a molecular sensor, is effectively a graphene field effect transistor, GFET. So going from a simple planar Hall effect device to, in this case, a liquid-gated FET. And graphene is incredibly sensitive to everything, whether you want it to be or not. And in this case, making a molecular sensor out of graphene and functionalizing that surface enables that transistor to be sensitive to a particular contaminant, say, in the liquid that's applied to the surface. And that's what this GFET molecular sensor platform is. It's developing our core 2D technology towards creating transistors. And at the same time, we're producing, if you like, a vertical product stream here, which is along that roadmap. So you can see that the strategy of the business is to, as we're building that know-how, as we're building that capability, as we're building the product complexity, we create verticals along the way. Because to jump from day one to some long-term computing aspirations is a bridge too far. But a business will look like this. It does look like this, with a foundry in the center, which is the core manufacturing capability for producing 2D materials and the surrounding technologies and processing technologies around it. And then, as we have today, the magnetic sensor and the molecular sensor products spinning from it. And that foundry not just supports our internal product development, but also supports partnerships with others. So as the 2D material momentum is growing, more partners will be using that foundry to incorporate what is our 2D material technology into their own designs. So where 2D materials have been modeled or envisaged in certain applications but not able to be produced, as nobody wanted to put the acetone bath in the fab, then we have an ability to start to incorporate what is our technology into those designs. And that's pretty much the model of the business. So how do we do that? How did we do that? Not the conventional route of coming out of the university. University of Cambridge has a lot of spin-out companies that go through a pretty well-trodden path through an incubator sort of facility or into the science park and beyond. If you're doing what I've just described, where your startup business needs to incorporate a number of MOCVD tools and front-end wafer processing and creating a clean room, you don't really fit into the science park or the traditional sort of incubator model that is full of software companies or fabless design houses. So we have to move a little bit further afield and trying to keep within the Cambridge area so that we didn't lose all our staff along the way. But in a rural location outside Cambridge, we built the first facility. And under seed funding, it's a pretty basic ground-up approach, taking what is effectively an almost derelict building through to fitting out the clean rooms that are now there over the last few years, incorporating the first MOCVD tools for 2D material deposition and all of the resulting R&D scale capability. which is a building about 30,000 square feet, which is now full to the brim with that equipment and people. Got up to about 120 people working around this technology in Somersham. And while that's been the workhorse for us to date, we're working to focus that building more on the ongoing R&D and pilot scale production, while we move our production and manufacturing foundry, as I described earlier, to the building that we took over in 2023, a short distance down the road in Huntingdon. For those of you that you recognise, it's still Cambridgeshire by the mountainous horizon in the background. So within that area, we're building. The photo on the left on the right is about a month old now. That's the clean room being constructed within that facility to be our manufacturing foundry. That will be online this year, with products then coming from both the facility in Somersham and the one here in Huntingdon. So to take that, to wrap up as a sort of a snapshot of that journey and what we've done over the 6 years since the initial establishment of Paragraph from Sir Colin Humphrey's group in University of Cambridge back in 2017-18, is to build that know-how and the process knowledge around, and the IP around the 2D material landscape, but not just to build that IP, but to build products and get them on the market based on that technology. And I talked briefly about the Hall sensors, the molecular sensors that we have now, and a further stream of our own products that are following on behind that. We've built commercial traction and development partners along the way, as well as some significant venture capital that we've had to do to fuel that growth and continue to fuel that growth. Building a fab is not just difficult, it's incredibly expensive. So we continue along that path and are now operating from 3 facilities, the 2 that I talked about in Cambridgeshire. And in addition, more recently, through acquisition, we have a facility in San Diego, California, which is focusing on the application of that molecular sensor into medical diagnostics. So San Diego is a cluster of med tech companies in California, and that part of the business is looking at use cases from the molecular sensing capabilities of graphene into those sort of markets. So 20 years since the sticky tape in Manchester is where we are now, and over the last 6 years we've built Paragraph to exploit that material technology, and it's our aim is to keep the UK at the forefront of the 2D material industry. Thank you very much.